Welcome you all to the Spark Research YouTube channel. This is Dr. V. Chandra, Assistant Professor in the Department of Electronics and Communication. And this is another session of this course, Analog and Digital Communication. And in this session particularly, we are going to take some questions which has been asked in GATE 2021. Particularly, that question belongs to the unit first and second. Right? So here is the overview of your analog and digital communication course, and in this session we are going to take the questions from this analog communication. Particularly the questions are belongs to the amplitude modulation and the angle modulations, right? So let's take the question. Question number first, this is question number 22. Consider a carrier signal which is amplitude modulated by a signal term sinusoidal message signal with a modulation index of 50%. Right? So modulation index is given. If the carrier and one of the sidebands are suppressed, carrier is also and one of the sideband is also suppressed, right? In modulated signal, the percentage of power saved. So power save means in normally in amplitude modulation, what are there? Both double bands are there, including the carrier. So now we are not only suppressing the carrier, but also we are going to suppress the one band. Means final, we are talking about the single side band. So how much power can we save if modulation index is 50%, right? So this is the question. So here is your original amplitude modulated wave. Here this is the carrier, and these are your side bands, right? And so question is that how can we find out the power? So power we can find like a square by t, amplitude a square by 2, right? So for carrier, for this one, a square by 2, and for like power that being used by this masses, that is m square by 2 if mt is your the amplitude, right? So this is the simple way to calculate. So we'll see, and as per your answer key provided, your answer is the fall in between the 92.2 to 94.6, 94.2 to 94.6, right? So let's see. Here is the some detail about the modulation index. Whenever we are talking about the modulation index, means suppose this is your amplitude modulated wave, right? So this is your, actually this is the carrier wave, right? This one, and these are your amplitude modulated wave. Masses will be the the envelope of this modulated wave. So here the the frequent the carrier wave is the varying the amplitude of your carrier wave, that is modulated wave, exactly is it varying from the certain range to the certain range. So if you know that range, then you can find the modulation index, that is difference of the V max to the V min. Like suppose this is the maximum voltage and here is the minimum voltage. Actually these voltages means amplitude is varying with respect to the masses, and divided by the addition of the V max and V min, right? So that is called the modulation index. Now what is the bands here? So here you can see this is the actually the message signal, and this is the modulated, that is mt cos omega ct, and here is the double bands, like the lower band and side bands both. So this like mt cos omega ct contains the both double bands, that is lower and side band. So in question what is asking that contains the only one band. So if it is one band, then how can we find out the power? So here are some more details. So A cos omega ct, this is your carrier. Mt cos omega ct, that contains the sideband. So the power belongs to this carrier is a square by 2, and power belongs to this sidebands is half m square by 2. Now you can find out the like useful power or the total power. So definitely total power means power contains by the carrier and power contains by the sideband, and useful power means only that power contains by the your sideband, right? So you can calculate and you can find out and you can get the value, right? So that is our question. So let's solve now. So first we will find out the total power. So if you will look into the previous slides, now you can also modify that formula, like you can find out total power is your carrier and plus the masses. So the in a short you can write PC, that is carrier power, and 1 plus mu square by 2, mu is your modulation index. In our question, modulation index is already given. So finally, if you put the value of mu, then you will get the 1.125, that is into the PC, that is PC belongs to the carrier power, right? Similarly, we can find out the power in the remaining signal, that is in SSB, right? So that will be your PC and then mu square by 4 in the only one band, so, right? So this will give you the power in a single band. So we got these values, power in a only one band. Now save power means the total power and minus the the sideband power. So that is this value. Now so percentage save this, the the save power and divided by the total power. So finally the answer is 94.44 percentage, right? So that's all. So here you can see now upper sideband contains almost the 5.55%, lower sideband also. Most of the power contains by the carrier power only. So no, that is why we are trying to avoid to send this carrier, right, along with this amplitude modulated wave. Otherwise, what is happening? Your power, most of the power like 90%, 88, 89% powers are totally wasted. Okay. Okay, let's go to the another question. Now, here one question. A sinusoidal message signal having root mean square value of 4 volt and frequency of 1 kilohertz is phased to the phase modulator with phase deviation constant 2 radian per volt. Right? If the carrier signal is CT is equal to twice of cos and omega CT, right? The maximum instantaneous frequency of the phase modulated signal is. So in this question, they are asking the maximum instantaneous frequency, right, for which phase modulated. So we the question belongs to the phase modulation, and here carrier is also given. So how can we find out? So actually, first of all, we have to find out the instantaneous frequency. Now question is that what is this instantaneous frequency? So in this phase modulation, your frequency will vary, right, according to the message signal. And how will it vary? Depending on the phase, right? So your phase will vary, and that is why your angle will also vary in a, so this is an also example of the angle modulation. So since phase is varying because of the message signals in this phase modulation, so that is why we have to find out the instantaneous angle, that is FIT, right? So that will be the your carrier and plus your masses, the Kp, and then dm by dt, right? So we will once we'll find out, and then we can put the values of the fc. You can find it from here, right? So that is twice by omega ct, that is 10 to the power 6. Okay, so that is our question. So let's find out. As per answer key, your answer should be in the range of the 0 10 11 310 hertz, right? So let's see. First question is that what is this phase modulation? So here you can see this is your message signal, the red color. This is the carrier frequency, and this is the phase modulation. So here your phase will be vary, right? So actually your frequency will vary in if since you are varying the phase, angle will because omega ct and plus your fcn plus your kp and then m of t. So kp is constant and m of t, the varying according to the message signal. So phase modulation can be defined as the process by which changing the phase of a carrier signal in accordance with the instantaneous amplitude of the message signal, right? So how can we write? So here is your theta t. Theta t will give you the angle, total angle. So omega ct plus kpmt. Now theta t divided by the dt. Actually, d theta divided by dt will give you the instantaneous frequency. That is our objectives to find. So d theta by dt, that will be the instantaneous, and we'll find out the omega c and find out the differentiation of kpmt with respect to t. Right. So that will give the deviation. So 5 fpm you can also write, this is the entire equation, that is a cos, and this is the actual the angle, that is the theta t. So that is exactly that one we are going to take the differentiation. Alternatively, you can also write your PM modulated signal, that is VC sine omega ct plus mt cos omega ct. So Kp and Mp both are constant, like both are similar terms. We are going to use this equation, right? So let's see. So here is your massive signal and then phase modulated signal, and so we will, all these parameters are given. That is RMS voltage is given, and massive frequency is also given. The phase deviation constant is also given, and then the carrier signal is also given, so carrier frequency is given. So we will find out the instantaneous frequency with this using this formula, and we'll find out the, okay, so let's find out. So here is the final calculations. So first, theta t, that is twice pi fc, that is omega ct, and plus kp mt, right? So this is the instantaneous angle of your phase modulation. Now find out the instantaneous frequency, that is d theta by dt. So that will be the d omega by dt. So if you want to get the direct frequency instead of the angular frequency, that is omega, then directly you can also divide by 1 by twice pi. So 1 by twice pi d theta by dt. Now just replace your theta with this and put it, and then get the differentiation, right? So here like also we can find out the peak amplitude, and like because we are going to formulate this m of t. So peak amplitude we can find out using the VRMS into a square root of 2. So here because the mt, you can get the value of am cos omega m into t. So like d of m divided by dt. So here we can get the differentiation of this, the ones we'll put the mt, that is am cos omega mt, then we can get this value, that is differentiation will be am into twice pi of fm, right? So these things will come out if you'll do the differentiation, and cos will convert into the sine, right? And so then we'll calculate the maximum possible frequency, like, so that will be your fc. So here the differentiation, if you'll put k, the m of t, so fc, that is the fc, and plus kp by twice pi, and then what is the differentiation of dm by dt. So here sine theta maximum, what will be the value of maximum sine theta, that is equal to 1. So am and twice pi fm. So finally f max will be fc plus k p am into fm, and we know the value of the kp, am, and fm. All the values are given, so put it, and then you can get the final f max, that is 1011313, right? So this is the final answer. Let's take one more question here from the superheterodyne receiver. So consider a superheterodyne receiver tuned to 600 kilohertz. If the local oscillator feeds 1000 kilohertz signal to the mixer, the image frequency is asking, right? So do not confuse in between the image frequency and intermediate frequency. Both are little bit different, right? So here, as per your question, what is given, the uh, the maximum, the local oscillator frequency, that is FLO, is given, and the tuning frequency is also given, that is your 600 kilohertz. So you can get the difference and collect the intermediate frequency, and then finally you can calculate the image frequency, that is fs plus twice of f if, right? So in this manner we can get. So let's talk about it, and as for answer key, your answer should be 1400. Some details about the superheterodyne before solving the question. In the image frequency you can find using this fs plus twice of flo, definitely. And this is your antenna suppose transmitting, and you are going to receive, right? So you can receive using the antenna, and then it will undergo to the radio frequency RF, that is tuning filter, and then local oscillator. With the help of local oscillator, here only FLO will be FS, that is and minus of FLO, and then it will cross to the IF stage filter, and IF, the is fixed to 455 kilohertz for your AM super heterodyne, and then further it will go to the detection, that is demodulator and the amplifier. In that manner you can convert, right? So this is the process. In more accurate, like you can go through this super heterodyne receiver, that is how the signal is receiving. So one signal will receive using the RF amplifier, then frequency converter will be used, and local oscillator will help, then IF amplifier, that is the intermediate amplifier, then detector, that is demodulation, and then deamplifier. So formula to use your image frequency, that is your FRF and plus twice of IF, right? And FIF, that is this intermediate frequency, you can get the difference of FRF and FLO, right? So like what is this antenna, all these details are here, you can check it, we have already discussed in our regular class. So let's find out the solution, right? So station frequency is given 600 kilohertz and local oscillator is given 1000 kilohertz. So calculate the intermediate frequency first using this FLO minus F of S, right? So station frequency, that is F of S, is already given. So that will be equal to the 400 kilohertz, right? Now calculate the image frequency using this Fs plus twice of IF, right? So Fs is your stationary, that is 600, and F of IF, like intermediate frequency, we already get the difference in between the Fs to FLO, that is 400, right? So if you put, you will get the values. Alternatively, you can also use this formula, that is image frequency is equal to the local oscillator F plus I of F, right? And in both manner, you can get the image frequency is of 1400 kilohertz. So that's all in this session. Thank you to join. If you have any doubts, please drop your comments. We'll take the questions.